Okay, so now I am recording the session. And as I was saying, this is going to be a little bit of a fast pass through this notebook, and you have in web class a video that explains this in a little bit more of detail. But the point here was to, as it says in the label, transform masks and top annotations into bounding boxes. This is the same data that we have been using for project number 2, and that some of you will use also for project number 3. As you will see, there are different possibilities for project number 3, so some of you will be using this same data, some of you will not. We have the same mosaics like this one, and here we are working with the label images that you have been working with, and with the 3 top annotations that we can show here, for example, in some detail. Okay. This is all very good for doing things like taking every center and then cutting a patch of the same size. That will be project number 3, version number 1, let's say, the regular version, and classifying those images. Deep learning classifier will consider each image, and its goal will be to tell me what class, what category that image belongs to. In the case of this project, it will tell me that this tree is one type of tree and that this other tree is another type of tree from just one single image. I will train and test that, and we will learn a lot about what it means. But most of the time, when I'm processing this type of data, this type of drone acquired tree images, what I want to do is not have to annotate all of the treetops, because those are notoriously difficult to annotate. So this tree is more or less clear. It's somewhere here, and this one is also pretty clear here. But telling apart where these trees are is really not easy. It looks like this is one, and probably this is another, and this is another. As you all remember, this is Sarah Kench's data, and while she was doing this annotation, she was telling me this is very difficult. It's sometimes not simple at all to tell apart how many trees there are. Nowadays, there is a student in the forestry group, someone called Vlad, who has been doing similar types of annotations, and he has actually ended up designing a whole system to do this properly that involves actually going to the forest and flying a mini drone so that he can check whether the point of conflict that he annotates on the drone image actually conform to what he sees in the drone image. And the difference between the information that you can see in the drone image and the information that you get from the ground level sometimes has significant differences. Okay, so most of the time we would like to have an automatic system that tells me where the trees are, not that I have to mark them directly on the image and then have them classified. Okay, so this is one more step. I want an artificial intelligence system, a deep learning system that does something more. The first one started from the image and the position of the points that I had to set manually. And the second one, the one that I want to, instead of an image classification network, it would also have an image classification part, but it would start from only the image, and it would have an object detection network. In this case, a tree detection part too. So it would first find where the trees are, then put a bounding box around the tree, and then classify and maybe even segment the tree. Segment means that if I have a bounding box that's here, it will have parts that correspond to the tree, but also parts that do not correspond to it, and it will be able to tell them apart. Okay. We will speak about classification, detection, and segmentation quite a lot more later in this unit. But the point is that I would like to have to train one of these networks that itself alone can tell where the trees are and classify and segment them. But in order to have that, as always happens with artificial intelligence, I need to have lots of correct answers to that. Okay? Artificial intelligence always needs to have lots and lots of examples in which to be trained on. Artificial intelligence has no power of deduction, no power of interpolation. It cannot go beyond repeating patterns. It can be very good at repeating patterns, even if the patterns are minute, even if the patterns are difficult for humans or for lay people to discern. It can really reproduce patterns that can be quite complicated, but it cannot make up anything new. Never. Anyone telling you differently is probably trying to sell you a subscription for an LLM, okay? So artificial intelligence can only reproduce patterns that humans give to it, okay? And then that reproduction can be really fast, and it can be really faithful in some cases if the training data, if the patterns that humans have given to it are good and well chosen and properly understood, not by the LLM. If the humans know how to prepare that training data, then the reproduction of the patterns can be quite something and very useful. But artificial intelligence cannot interpolate, extrapolate, cannot deduce, cannot think in any, let's say, minimally workable definition of the term. So in order to create that information to detect objects, I need to tell to my deep learning model not only the position of many trees, but also the bounding boxes of where the trees are, because that's what I want my model to end up predicting. Not only there is a tree here, but also there is a box that contains a tree here. In our case, we had, the label image showing where each tree species was, but that did not separate the trees. For example, all of this blue part are trees of the same species, but here I do not have the points, so I don't know where every tree is, and even when I add the points, I do not know where the bounding boxes are. So what I'm presenting here is just a relatively simple software to move from those two informations, from me knowing that this is all the same tree species and that there are these trees here, to having the bounding boxes for every tree. I can do it manually, but that's a lot of trees and that's very long and tedious. And I can approximate the same thing using computer vision. As you will see, in order to do that, I need to use some advanced library functions. But with your programming language, you already have a good leg up to do that. So let me give you a few more details, and if you want all of them, you have the previous video that I mentioned, okay? So we have this list from binary function that you already had that uses the connected components with stats function from OpenCV. So here I'm using a function that takes the binary image that's made up of a white background and the black dots for the position of every tree, and using that connected components with stats function, I get a centroid for every point. So that from something that's an image, I get a list of coordinates of X and Y about where my centroids are, okay? And then I can also know, if I know the coordinates of one particular center, and I go to the label image, I can also know what species that one belongs to. I look at the label image, I look at the value of my XY coordinates, check that pixel, and see what tree species it belongs to, okay? Not only that, but I know what part of the image around the point that I have chosen belongs to the tree species. And that's what I'm going to try to do, okay? I'm basically going to use two approaches to separating each region that contains trees, knowing what the centers of those trees are. I'm going to assign bounding boxes to all of those trees, okay? If I only have one tree, that's very easy, okay? Let's suppose this guy is from species and it's isolated. Then I just put a bounding box around the whole region if there is only one tree. So that's pretty simple. But if I have more than one tree in the same region, then it's a little bit more complicated. Where do I put the bounding box? Here? Is this going to go all the way down there? Is this going to be marked or not? And if I have a region with many, many trees, then that becomes very tricky because my bounding boxes for the different trees should overlap as little as possible, okay? I'm going to use two approaches. The first one is going to be called the Voronoi diagram. The Voronoi diagram, you can look it up, but it's basically a space partitioning technique from computational geometry that takes a region, this one, and a series of sites, and then assigns to each site a cell saying these points are closer to this point than any other point. So I have these sites and I'm going to choose to find the set of points in the region that are closer to this site than to any other of my sites, okay? And we can have a graphical example here, okay? Let me see. Yes, we have an interactive visualization here. Yes, I am going to set up one point here. This is an interactive visualization of the Voronoi diagram. When I have only one site, all of my space, all of the points are closer to this site than to any other because there is only one of them. If I set the second site, then I get a partition of a space. I do the distance between the 2 points, the line that unites them, a perpendicular line, and then anyone on this side is closer to this side. Sorry, anyone on this side is closer to this site, and anyone on this other side of the hyperplane is closer to that one. Okay, and if I set another site, then I have another cell and another and another and another and another and another and another. Okay, so this is a cool mathematical data structure where I am only doing this thing. I find the sites that are close to the new site that I have decided to the hyperplanes and break them down, and I end up building this kind of complex diagram. This visualization is very cool, and I can even drag and drop and see what would happen if I left a point at different places, okay? That is the Voronoi diagram. It's a mathematical structure. It's slightly difficult to understand at first, but not so much. And it gets very, very complicated. It can have lots of generalizations. I have nearest Voronoi diagram like I have been doing, but I also have furthest. I can put weights to this side, like saying, okay, this is not only going to be the nearest points, but if any point is closer, is less than twice as close to any other side, still I'm going to make this the preferred one, okay? So there are lots of generalizations. But basically what this diagram does is that it partitions space. And I'm doing something relatively complicated, but that I can import and implement very easily using libraries. If I had to code the Voronoi diagram from zero, that would be a hassle and that would be long. Believe me, I have done it, okay? But I don't need to because I can just import the Voronoi library from, for example, CPy spatial, and then I get very simply from a set of points, not as pretty as before, but a Voronoi diagram with my sites, okay? Here I have the unbounded side, so there are always cells that are infinite in theory, which are not shown here because I conveniently, the author of this conveniently cut the space very close, okay? But I have all of those cells that I can manipulate that I can use, okay? I did this a couple of years ago by just Googling and downloading this. You can also ask an LLM and you will get something that probably will work just fine, okay? And now I want to use this theoretical structure for my practical problem. And what I want to do is say, okay, I'm going to take this partition of my 3 regions and I'm going to consider this, make the Voronoi partition here, and make the bounding boxes using those, okay? And again, take some time to look at this and to watch the previous video, but after some wrangling, that is exactly what I get, okay? I took the 3 tops as sides, I computed the Voronoi cells, and then I only visualized the proper region. So for example, this is a whole Voronoi cell, but this tree is alone, so the bounding box is going to be just here. Okay. In this case, where I have many trees in the same region, then I'm going to consider the part of the Voronoi cell that corresponds to this tree, and I'm going to put a box around it. And this code does it. Okay. Word of advice, this code is slightly heavy, so if you want to run it in Colab, you're going to have some problems. That's the root of my problems, and that I was trying to run it on my own computer, but there I have some installation thing, so I cannot show you the full code today, but you have it in the video, and you can download it into your computer, and if you have the same installation problem, let me know, and I will tell you. The point is that I end up with all of these boxes automatically computed, and you have all of the code here. If you can jump the annoying installation problems, okay? If you can solve them. So that's a very, let's say, theoretical way to solve the problem. It uses slightly complex mathematical structures, and it does something better than I could do without this automatic type of computation. You can do it using relatively simple Python code. If you know what you're doing, you can implement this, you can be careful with every step, and you can get to visualizing to completing this code. And for one thing like this, for example, using an LLM can help you quite a lot to find the right library to debug if your results are what they are supposed to be, okay? I'm not going to stop a lot into this, but when I saw this, I was not super happy because I had lots of overlap between the different Voronoi boxes. The Voronoi boxes were a little bit too big for my liking. For isolated trees or trees that are in quite small connected component regions, the thing was very good, okay? So all of these Voronoi boxes are pretty okay. Even this one is not too bad. There is an overlap between these 2 boxes, but not terrible. But as soon as I get to more densely populated regions, I get things like these 2. This guy has a Voronoi box that almost contains the neighboring point, and this one has a huge Voronoi box that contains 3 points. So that's annoying. So in addition to using that, I use something called the distance transform. And the distance transform basically computes the distance from any point in my mask, so here, to the outside of the mask, okay? So basically, if I make a bounding box based on the distance transform, I'm going to make a bounding box to the point in the outside that's closer. So for example, here it's going to be likely this point from here, so I will have a very small bounding box here, okay? The point that is closer to the outside here is something like this one, and I'm going to have a smaller bounding box here that will always contain the center point and just go to the first point outside. And here it's going to end up being much smaller than the Voronoi boxes. For the rest of the code, I do that and I get tighter Voronoi boxes, and then I combine the 2 approaches. I take boxes that are not as big as the Voronoi boxes and not as small as the smaller boxes, but that combine the 2. And that was very useful, and you can actually use that in one of the results of that in one of project 3 formulation. My point here is that you can use some pretty advanced theoretical concepts with Python if you know what you're doing, if you know about those concepts with relatively simple code. This notebook, I am not explaining it now, but you can already understand it. You don't have to. I would advise you to have a quick look to see mostly what's going on, but you don't have to follow all the functions and all the things because probably you're not going to be solving this very problem. But I hope that I give you an idea that even if you have a complicated problem, if your project requires something that's, let's say, theoretically advanced, if it has been implemented in Python, you can use the functions that someone else has already programmed to get the results of that without having to do everything from scratch. And today, thanks to LLM coding tools, then you are likely to be able to do that more or less quickly. Again, as usual, with the caveat that you have to be very careful and that you still need to know what you're doing. Otherwise, the LLM is going to be useless and probably worse than useless, lead you astray. Okay, but with the right combination of knowing what you're doing and using coding tools for the simpler tasks to speed up your coding, you can use this type of complex data structures. Okay, if you're an experienced coder, you have already done that. Do not let yourself be tricked by the LLMs. If you're not, if you're just learning to code, probably do not start by something super complicated, but know that if you want to do something a little bit more difficult, probably you can get there eventually with some time and some patience. Okay. Well, so that was it for this, let's say, final thing to say about computer vision. It can get complicated. Even if it does, you can do it. It will take some time. You will need some help from someone who knows how to code, and maybe you can substitute some of that by using some LLM coding tool, and then you will eventually get there and you can use even very complex theoretical data structures, theoretical concepts in your research project using Python and using coding. Okay, doesn't have to be easy, but my point is that you can. Actually, some of the students in this course last year are doing just that and are doing some amazing and pretty complicated things using Python. And I encourage you to try to do the same and to make the most of the effort that you have been doing in the course. Okay. Again, I don't know if there is any question at this moment. If not, I'm going to move on and to talk a little bit about history, the history of deep learning, and the history of AI after a brief speed run about, again, what AI is. Not at the moment. Okay. Okay, so let me move on to this next presentation. Not this way. Exchange, I think. Yeah. So I gave this presentation a couple of years ago, not a couple of years ago, last year in Turin in a visit. So I hope none of you have already seen it. If you have, it's not going to be super long. But I call this deep learning speed run to just give a brief glimpse of what deep learning is to help me focus the rest of the discussion for the rest of the unit. Deep learning is a part of artificial intelligence. Artificial intelligence is a term that was coined, as we will see in a second, a while back. Many of us, many of you have learned about artificial intelligence in relatively recent years. When I ask this question in some high school activities that I do, high school kids think AI was invented. Many high school kids, some are very well informed, but most of them think AI was invented something like, I don't know, 2016 or 2020 sometimes. Okay. It was actually the term coined way back. And as I will make the point in a second, it can be traced back to all the way down to when people started creating machines, because the goal is to try to get machines to do things that humans do better. So artificial intelligence has been going on for a long, 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 long time. And deep learning is just one part of all of the versions that exist of artificial intelligence. Some of them we don't consider them artificial intelligence anymore. Deep learning we do. But deep learning is just one part. Deep learning contains the image classifiers that we will be using for the main part of Project 3, the object detectors that I have already commented on, image segmenters that we will also talk about, and also the natural language processing networks that are the basis of LLMs, of ChatGPT. LLM means large language model, and ChatGPT, Gemini, Claude, everything that's used in GitHub Copilot, all of those are LLMs. And usually using transformer architecture, deep learning models, deep learning natural language processing models. Okay. So it's an important part nowadays, but it's just one part in artificial intelligence. Which can, as we said before, process data very fast and find and reproduce patterns, even those that are very faint for humans. Most of what motivates the current rise in artificial intelligence comes from medical imaging. Training a doctor to find cancer in mammography is very expensive and takes a lot of time. 10-year doctor with 10 years experience doing that does way more work than 10 doctors with 1 year experience. And because of that, they make the big money and they are very, very valuable. What motivated artificial intelligence research at the beginning was to try to reproduce some of that expert knowledge. And artificial intelligence can get very good at it. It can never substitute humans. And how we use it alongside humans in important contexts, like, for example, medicine, is a very important part of AI ethics. I will speak about ethics from time to time. The important part today about ethics is that it has not been properly regulated and it needs to. And companies and media are telling us about the rights of AI if AI becomes intelligent, and that's nonsense. That is just because it's not going to happen anytime soon. Probably it's never going to happen, at least with the current models. AI is not intelligent. It's not getting intelligent. It will not become intelligent next year, not in 10 years times, unless someone comes up with some completely different type of model. That's bullshit. And that's interested bullshit. The important ethical part about AI today is whose data is AI trained on. Does that data really belong to the company? Should they be using it? Is the data used reinforcing society's biases against nationalities, against particular people because of, I don't know, race, sexual orientation, gender, whatever? Not only that, but what is artificial intelligence used for? Is it used for something that's nefarious? Is it used for surveilling the population or for stealing money from whoever? Okay, not even only that. If I'm going to use artificial intelligence in medicine, am I going to use it instead of doctors? What happens if the AI system makes a mistake? Am I going to use it alongside one very overworked doctor who can now realistically supervise the results of all of the, let's say, AI systems that are being used alongside them, and then just use a human to be blamed if the artificial intelligence systems fails? Or am I going to use it in a responsible manner where a sufficient number of experienced doctors use those systems to speed up their expert work, but still have enough fail-safes and enough redundancy between them, between the humans, to make sure that the probability of someone being misdiagnosed is actually very small. Okay? All of those are very important ethical concerns with AI today. But if I can obviate them, if we as a society can find a way to navigate them, to find a way that works for us in a way that is acceptable, then AI can be a very useful tool. It can find patterns very, very fast, and it can speed up the work of some humans if we set up the conditions properly. Especially because it's very flexible and it can be used to solve many, many different problems. Okay. For example, we are using it to find kanji in these ancient Wasan documents from the Edo period. And if you want, if you're interested in this, you can also work with this type of data for project number 3. Okay, we have different characters and we want to find where they are. So we want to do object detection again here, kanji detection here, or character detection, because these are kanji and there are katakana and hiragana characters somewhere too. So because it's a very flexible type of imaging, it can be used for this too. And for, as I said before, image classification. I can use my drone images and I can, if I give it the position of the trees and bushes in this case, I can classify them into different species. Or if I have enough object detection data, hopefully the system can do everything, can find and then classify the systems on it, the tree species and positions on its own. Okay. But AI cannot think in any way. Not now, not soon. And anyone telling you differently, in my opinion, I have followed this. I'm very interested in this. General artificial intelligence is not a thing. And there is lots of bad faith with this. As I will say in a second, nowadays, the way we experience artificial intelligence is through products that are worth lots of money. And there's lots of people interested in selling them to us. So do not believe many of the things that you hear because most of them are not true. So artificial intelligence, deep learning, LLMs cannot think in any definition of the term that's minimally respectable. It cannot go beyond its training data. So you need lots of data to create a model that uses this deep learning paradigm, these artificial intelligence ideas. And once you have done that, if you have enough data, you can do exactly what the data shows. That and only that. Simple thing. If I train a system to tell apart 250 images of dogs, I have done that. Species of dogs, different species of dogs. Some of them can be very, very similar. The system, if I have enough data, will become very, very good at that. In some situations, better than humans. And in all situations, better than humans that are not expert at the task. We will speak about this today in a little bit. But it cannot go beyond its training data. If that system that's very, very good at classifying dog species gets an image of a cat, it will not say this is a cat. It will not even say this is not a dog. It will just say this is a dog of one of the species, because it cannot go beyond its training data. Okay. And AI systems cannot do anything without lots of high quality annotations by human experts. Okay. AI does not generate new information. It can be used, well, let's not go there. Okay. Basically, for the uses that we're going to see and for most practical uses, AI cannot generate information that's not already in the training data. And think about what that even means for things like LLMs, okay? LLMs cannot think anything new, of course, but are only trying to reproduce the information that they have on the training data. And no one knows, well, no one. the companies know, but users do not know what data LLMs have been trained on. Okay, so that means that depending on the use that you want to give to an LLM, the training data can be quite far from that. So the answers that you're getting in some occasions can really not be what you hope them to be, because it's very difficult to create products that are supposed to solve everything, anything that can come up to the mind of every human on Earth. If you're doing tasks like, let's find information on the internet, that's probably doable, probably can be trained to a reasonable extent. If, let's say, I'm going to invent a new language, probably that's not going to be something that the LLM is going to be good at, or just reasonably able to produce a result that's reasonable by most definitions. Okay. The point is that these LLMs, I mentioned some before, Midjourney here is another one that generates, and DALL-E that generate images also from prompts or from other images or whatever, okay? And one thing that we have to remember is this, these things are all products, so they have many limitations. This is an example that I like. This is from last year, and this is from the same prompt from to the same Midjourney LLM. This LLM receives an image and receives a textual prompt and then creates an image. The image in the left with this, let's say, Japanese looking illustration, Japanese style looking illustration, and even some sort of slightly Japanese temple-y thing looking here, although if you zoom into it, it's actually pretty bad, but and proportions do not match, and this thing has kind of three roofs intersecting in a place which doesn't make any sense, but still, if I look at it from afar and don't interrogate it further, this looks a little bit like a Japanese style thing with kind of sakura looking flowers and so on. And this girl here is the answer that one of my Japanese students got from her prompt. The student is a young Japanese woman who likes this type of illustration. And when she asked for a picture of a cute girl, she got this image. I was interested by that, and I, on the same day, made the same prompt to Midjourney, and I got a completely different image. I got 47 at the time year old male Western guy. I got this completely different image. Okay, I was actually kind of happy because I was worried it might. I did it not online in class because I was worried it might go onto the site of young woman with very little clothes on, but no, because I have young children at home, it went this way. And the cute young girl is a child playing with some plush toys and, well, quite a lot of too many frills and the type of illustration I really don't like. But the point is that why did I get such a different illustration that from my young female Japanese student? And the reason is that these things are products and they have a profile on you from the prompts that you make every day, from your information that the company selling these products has gathered from not only your history, but I don't know, from other tools that they have that you have used, from information that has been sold to them by other parties that do have your information that you have inputted in the internet at any point, that you have Googled at some point too, depending on who owns the application that you have used. These tools create a profile of you using as much information as they can get, and then they try to create prompts that keep you coming back for more prompts all the time. Okay, so in this case, the profile of my female student said she was a young woman who liked this type of picture because probably she had Googled them at some point and she had visited pages with this type of illustration, and that's what she got. Probably my profile says my age and gender and the fact that I have young children because I have probably Googled, I don't know, toys for 6 and 8 year olds. And well, they are all a little bit older now, but um, because of that information that the company can conceivably have gained from me, I get a completely different answer. And this is very illustrative, but that is happening to you every time you type anything into ChatGPT. And that's not artificial intelligence, that's marketing. So any response that you get from those systems is also colored by that. That has nothing to do with the system thinking. This is just a marketing team linking that information that they keep building all the time to try to serve you with whatever the marketing team thinks is going to keep you coming and asking for more prompts and paying for their products. Okay, so there is artificial intelligence part of all of this, and be very careful because there is a very important product side of things to this. When they tell you about AI rights and so on, they are not really worried about robots getting actually intelligent and needing to be protected because, as I was saying, no one is really thinking, well, I don't think anyone in industry is thinking that's going to happen at any moment soon. But these type of things of keeping a profile of you and using that to modify the output of the LLM tools that they are selling is a little bit of a gray area, is a little bit murky. Should we let them do that? They do not want that regulated, so let's regulate something else. Okay. How to use AI for research, and that's probably the main goal for this third part of the subject. There is one very important thing, and we will speak about this more, not next week, but the day that we speak about training and this thing about validation and training sets. The problem is that we are trying to do two things at the same time when we use AI and deep learning in research. Okay. The first one is like a data modeling problem. Like when we have a cloud of points and we try to fit a line in between them, that's called linear regression. And that model fitting, putting a line in between the points, is essentially the same thing that is done with artificial intelligence today. Of course, with many, many more parameters, but that's a formal model. I have a set of data in a high dimensional space and I want to fit a model to that data. And fitting the model means minimizing a loss function, a mathematical function, and getting that using a gradient descent optimizer. So all of those concepts, model, loss function, optimizer, all of those are mathematical concepts. Okay. So that's one of the problems that I'm trying to solve. The second problem that I'm trying to solve is something real. Finding the kanji, classifying the trees, finding the trees. Okay? And the hope is that solving the first one is going to help me or to automatically solve the second, but that's not always a given. And that's something that many people do not understand. There are three data sets involved in research when I use artificial intelligence. Training and validation data sets are used for fine-tuning the model and preventing overfitting. We'll talk more about this later, but basically they solve problem number one, the mathematical problem, the one where I fit a model. The testing set number three, sorry, is used to solve the practical problem, to estimate practical problem performance. I think this is not very clear here, but it says estimate practical performance. So with the testing set, what I'm trying to do is, after I have solved the theoretical problem, can I actually use the result, that model that I have trained, to really find the kanji in a new page, to really identify trees correctly in their species if I get new data. The distinction between these two sets is often not clear in published papers. Okay, between these two steps, between the theoretical part and the practical part. And it's all that matters when you want to use this for anything practical. Okay, so that's very important. And these considerations are also usually not well understood in mass media and in discussions about, for example, LLMs. Okay, how is training data used? How is training data created? What is the goal of the training data? Because training and validation absolutely determines the practical results. If you do not solve the first problem properly, then there is no way on earth that you're also going to be able to solve the second one. If you solve the first problem, maybe you also cannot use your results for practice. That's overfitting. That might also happen, okay? But if you don't solve the first problem properly, if you don't decide the training and validation sets properly and train the model correctly, then there is nothing you can do. Even if you do that, then you still might have bad luck and not be able to use what you have done for a proper practical use. Okay. Sorry. Let's jump now to the second presentation. I'm of course speaking too much, but I do have still some time.
Sorry, I don't want to steal the little time you have left, but I would like to ask a couple
Yes,
of
go
questions,
ahead, please.
if possible. So you said that to properly train a model, we would need lots of correct examples that we know are correct from human expertise.
Yes.
Expertise, sorry. But let's say, keeping the talk about the Voroid example that you brought in the notebook, I mean, how much is lots of examples? Because, for example, if we take our data set from the last project and using it as a reference to quantify the amount of exact and correct data that we've got, would you think that that would be enough for a decent training from your experience, or that's not even close?
That is a very good question, and that's a very pertinent question, and that's one that I'm trying to. So there is no easy answer to this. Okay, I put a lot of data there to provoke that sort of reaction. I'm devious like that. Let me. I will go a little bit deeper into this in this history part, but the short answer is it depends how much data you need. It depends on how difficult your problem is. Okay. So, for example, we saw before. Let me see if I can get back to it. Yes, I can get back to it pretty quickly. So let me break this one. And I have this one. Yeah. So this is from a student from, I think, Marco Conciatori. I think he's from Parma. Okay, which who was all, we published a paper with him recently, and he was doing image classification. In this case, there are different species of trees and bushes, and we have autumn data. So luckily for us, some of the trees are green, like these fir trees. In the pictures that we have, and some of them have very bright colors. So this is red and this is yellow. So in this case, doing this classification makes it easier. So because the different classes are easier to tell apart, classifying them correctly needs less training data, a smaller amount of training data. This small amount of training data can be as low as 10 images for some very simple problems. Okay. Then again, with this, some of the same species, but with images that are from summer where everything is green, then that becomes much more difficult. We have another paper from 2024 where we needed in this case, I think we had a couple of hundred images and we got accuracies of, on a very simple example, 98%, 99%, so completely done. With the images that were only summer, we needed thousands of them, and we only got to something like 85, 80 something percent. Okay, so the difficulty of the problem, how similar the classes are, heavily determines the data that you need. Not only that, for example, image classification problems, you're only trying to assign one label to each image. That's relatively simple information. You only need one code for every image. If you need to find the coordinates and then segment and say these pixels are 3 and these pixels here are not 3, then that makes it more difficult and you need more information. Okay? Then, before you start, can you guess how much data you're going to need? Not reliably. Okay? Because I have been doing for a few years, I can have a, let's say, ballpark estimation, depending on the problem, if that's going to be something that's going to be easy or difficult. But even I get it wrong sometimes. When I said lots of data before, I was cheating a little bit. Artificial intelligence has been going on for a long time. And until the 1980s, lots of data for pretty much any problem meant having a huge team of people collecting data for years. Okay? The popularity of deep learning now is that that's no longer the case. Nowadays, with relatively small amounts of data, hundreds, a few thousands of data, many problems can be solved. Okay? So, for example, for a master thesis, can you collect enough data to train effective deep learning model through a master thesis? Yes, it has been done before. Many people have done it. Will any master thesis project do? No, most definitely they will not. Depending on the problem that you choose, you will have more or less effectiveness depending on with a, let's say, reasonable amount of data that you can collect and annotate, because annotating is very important here during the duration of a master thesis. Okay, so no easy answer, depends on the problem. Likely, so this is usable, this is being used continuously in this type of a scenario, and usually it's at the very least hundreds and most of the time thousands of annotations. Okay. I hope that answers the question.
Yeah, definitely. Can I ask another question?
Please.
That's a shorter one. Just we hear a lot of talk about LLMs hallucinating, but I haven't understood what that means yet.
Let me see 1 second. I think I have an example. Well, I definitely do have an example. Let me see if I can find it quickly, is the point. Yes, I have it here. No, that's not an example of an hallucination. So, well, let me just paraphrase it. I have somewhere a slide with exactly that, but I don't have it now at the moment. I asked ChatGPT a couple of years back because this was a subject where I tried to explain to people who are not even who are from the Faculty of Science and other faculties who might not know much about programming or anything at all, and just come to AI from a background that might not be science. And I ask these LLMs different things and so on. I asked ChatGPT to tell me how to ask for the post office in Japan. Okay. And then I got a pretty decent answer in Japanese about how to ask for the post office, and that was. But then there had some problems. We looked at those. But then I did the same thing, and I asked the ChatGPT to ask for directions to the post office in Ulldecona, which is a village in Catalonia where I'm from. Okay, and the thing answered the query in French. So I was supposed to go to Ulldecona in Catalonia and ask for the post office in French, which surprised me. And I said, okay, why should I use French in Ulldecona, where I know that people speak Catalan and Spanish, but usually not French. Not many people speak French there, if at all. Then I got a very lengthy discussion about Catalonia being part of a county from France during the Middle Ages, and that resulting in many people in that particular village speaking French nowadays. So the LLM said um, that the main language in the village was actually French because of all that history. I was really surprised about that, and then asked the same thing about my hometown. And the LLM said that yes, French was also the most widely spoken language there. I asked for references and I got 7 different links to the history of the place and the reasons why that French is the most spoken language there. And the important point there is that that is all complete and utter bullshit. French is not the most spoken language in Ulldecona, in my hometown Banyoles, or anywhere in Catalonia. That was all what we call a hallucination. Okay. The term is a little bit, let's say, misleading because it tends to humanize the LLM. Okay, it's very easy to do because the way the software works, it makes you think you're speaking to a person because the chat is kind of informal, and then you get all of these personal cues. So the companies designed this to make you think that you're speaking to someone. That there is actually some entity, someone thinking, answering. There is not. It's just a tool to process language and to predict the sentence that you want to read. Okay, that's what they are trying to do. And sometimes in that prediction, the system gets confused and reads from some sources that contain incorrect information and then creates all of those. And then when it has started in that way, it continues in that way and tries to complete what it has already been doing and to predict the next plausible sentence from what it has already written. So once it made the mistake of writing the answer in French, of asking for directions in French, then it was trying to justify all of that through increasingly complicated wrong information and false information. Okay? That's what they call a hallucination. It looks like someone being on drugs and getting increasingly hung up on a weird explanation. That's not really what's happening. It's just about this prediction of the more likely sentence. And if you have already said that French is the most spoken language, then when they ask you why, then it's more likely that you answer because and then give some explanation that justifies the thing before than that you stop and say, no, that was wrong. Okay? Because LLMs have no concept of truth or falsehood anywhere inside of their training, and they cannot have it because of the type of architecture that they use them. Then they get sometimes lost and hung up in this kind of weird cycles of falsehood. That's what is called a hallucination. Although the term itself is a little bit tricky because it seems to imply that there is someone hallucinating where there is really no one. Okay, I will look up the examples and I will show you a little bit more about them in later classes. Okay.
Thank you.
Anything else? Okay, so let me continue. I have 10 more minutes. These questions are really very interesting. So as I said before, we have quite a lot of freedom to do whatever we want, okay? So I'm much more interested in knowing what you want to hear about than just repeating what I always say, okay? Okay, so about history, and I'm going to continue this next week, but I'm still going to try to do this a little bit fast. I'm going to cite from different people about the history of AI, because I said before, deep learning is just a small part of AI. They define the concept of AI as the study of how to make computers do things at which at the moment people are better. And if we even say machines, then we can trace the evolution of this very, very far back. This is a picture of one toy from my kids, and that's my own hand. So this is a very small drone. So this thing can fly. So it can do something that we can never do on our own. This is a machine that can do something beyond our human capacities. Okay, and it costs 1,000 yen, and it's very simple to use. When we try to make computers that can, in some sense, in some respect, think or achieve some kind of result that we usually achieve by thinking, then that becomes suddenly very, very scary. Okay. And I am not sure why that is, but that is part of the problem with AI and part of the mystique surrounding it nowadays. If we think about machines that help us think, we can go really, really way back to the invention of logic. There are medieval treatises on what a machine for thinking would look like. Lots of history about calculating machines, culminating with the invention of, let's say, programmable machines like the Jacquard looms that were made to build textiles, but could be seen as a early precursor of modern computers. And then Ada Lovelace and Charles Babbage with the invention of actually programmable computers, difference engines, they used to call them. And the first person to realize that those machines could be then made to do general things and could be programmable was Ada Lovelace, who is the daughter of very prominent Lord Byron. She's probably more important to the history of humanity herself, and she is the mom of all programmers. Okay, so female people, if anyone tells you that programming is a man's job, well, we might be majority now, but women programmers have just been ignored by history. It doesn't mean they were not there. It doesn't mean they were probably the drivers of the whole thing for most of the most important points. Okay. That went in parallel with the development of the theory between the, let's say, mathematics of thinking. Hilbert's completeness program, Gödel's indecisibility propositions and theorems, and Turing's machines and Turing's work. So there has been a long history of theoretical developments on how to think and on machines that aimed at thinking, okay? And that from 1945 resulted in the first computers. And you can check the history of the first back, also involving Grace Hopper, another very prominent female programmer, and for some reason, admiral of the US Navy there, okay? And the definition of why that's called a bug, and that's from 1946. From there on, things got academic, and the definition of artificial intelligence of the term is actually from 1955. So not 100 years yet, but we are getting there. That's the actual discipline that we are going to be working in. That whole thing started as early as the computers. And the first golden age of artificial intelligence happened almost immediately as soon as the term was created. And there were all these very prominent people, the leading professors in American universities, making all of these promises or predictions. Things like Turing, Alan Turing, the great calculability scholar, saying in about 50 years, an average interrogator will not have more than 60% chance of correctly assessing the Turing test, where, let's say, in a very quick formulation, you chat with an entity on a computer and you as a human have to tell if the other thing is a chatbot or is a person, okay? Turing said that that would be done by the year 2000. there were predictions about chess computers becoming world champions, discovering new mathematical theorems, or in 1965, Simon, who was very prominent too, said that in about 20 years, machines would be able to do any work a man can do. In the 50s, 60s, and 70s, artificial intelligence people were promising these things. Within a generation, the problem of creating artificial intelligence, and we would call that general artificial intelligence today, not narrow, but a computer that can truly think like we think, they said that it would be substantially solved in a generation. Okay, that led to a golden age of investment, especially in AI, and that in its turn triggered a golden age in areas like robotics, computer vision, reasoning, and of course AI and human language processing machines, things like Elisa, Prolog. Not going to step on them today. And also games, for example, how computers could play chess or checkers or even Go. Okay, but that did not actually live up to the hype. For example, this thing about the Turing test, would you be able to tell if you were talking to a human or to a chatbot nowadays? Well, I'm not sure. There is no serious competition of this anymore. But let's say that now, from 2022, 3 on, all of these LLMs have gotten pretty good. But before that, it had not been done. So if this has happened, it happened later than was originally predicted. The world champion thing did happen in 1997. So that was something that ended up happening, but it was like 40 years instead of 10. The discover and prove a new mathematical theorem has not really happened in the meaning that was implied at the moment, although AI has been used by humans to help them prove new theorems. So it's a little bit hard to say. It has had a significant effect, even though not as a general thing. Any work a man can do, not any work, not anytime soon. But the list of works that AI systems can do does keep growing. Maybe not to in not such a long time we will add the work of driver to the list of driving cars, driving maybe piloting planes to the list of work that AI can do. Okay, and the generation of general artificial intelligence, people are working on it a lot. It's not anytime soon. Okay, the average intelligence of a human being, well, what the hell is an average intelligence? But still, no, not general intelligence in any case. Okay, all of that, let me jump a little bit forward, led to what is called an AI winter. All of those promises that did not live up to the hype led to a long time where AI was perceived of something of a past technology. In 1996, there was a negative report on machine translation that killed much of natural language processing work for many, many, many years. Probably if that report hadn't happened, we could have had maybe LLMs and so on much earlier. Did we want them earlier? I'm not sure we want them now. So that happened the way it happened, okay? There were limitations of the AI models highlighted in a paper in 1969 by Minsky, and those still hold. And those are the reasons why I say so conclusively that general artificial intelligence is not happening anytime soon, okay? And then ethical, philosophical projects started appearing. There were some huge projects like the Japanese fifth generation project that did not produce the results that were expected. All of that is nicely summed up by a book from 1989 by Roger Penrose, eminent physicist, called The Emperor's New Mind. I don't know if I'm going to finish with this today. If you have heard that children's tale called The Emperor's New Clothes. That is a kid's tale where an emperor has it all and wants to show their richness and how they are the most powerful emperor on earth. And they commission one set of clothes, one gown that is going to be so impressive that everyone will see that that is the most powerful person on earth. And what they get in the end is a very smart tailor that tells the emperor that they have brought him this very, very impressive gown that only extremely smart people can see. And all the rest of the people just will not be able to see the dress. The emperor pretends, of course, sees nothing, pretends to wear the dress and parades himself naked while everyone says, oh, yes, that is a very fine piece of clothing, because no one wants to be proven not to understand, not to see, not to be smart enough for what's happening. Until, of course, proverbial little kid points out that the emperor is naked. Roger Penrose made the point in 1989 that all of that generation created really huge expectations around the production of artificial intelligence that were basically baseless or were extremely limited. And I think up to a point we're still there. Okay? Is that it? Should we stop talking about that? Well, no, because there is more after that. But today I have run out of time. So not tomorrow, next week, I will continue with this and we will also speak a little bit about data sets. Thanks everyone for listening, and we will finish the session right here.
Thank you.
Thank you.
Thank you.